Listening Practice, Chapter 1, Introduction to AR and VR 1.1 Defining Augmented Reality, AR. Augmented reality, AR, overlays digital content, such as images, sounds, or text, onto the physical world, enhancing the user's perception of reality. Unlike immersive virtual environments, AR integrates digital elements into real-world settings, often through devices like smartphones, for example, Pokémon Go, tablets, or AR glasses, for example, Microsoft HoloLens. Key characteristics include contextual interaction. Digital content responds to real-world environments, for example, furniture placed virtually in a room via IKEA Place. Device flexibility, works on screens, mobile AR, or transparent displays, headsets. Use cases, navigation, for example, GPS arrows on windshields, retail, virtual try-ons, and industrial maintenance, overlaying repair instructions. 1.2 Defining virtual reality, VR. Virtual reality, VR, immerses users in a fully digital environment, disconnecting them from the physical world. This is achieved through headsets, for example, Meta Quest 3, HTC Vive, that block out external stimuli and simulate 3D spaces. Core features include full immersion, 360 degrees visual /audio environments. Interaction tools, hand controllers, haptic feedback, and body tracking, for example, *Valve Index. Applications, gaming, Beat Saber, virtual training, flight simulations, and therapeutic uses, exposure therapy for phobias. 1.3 The spectrum of mixed reality, MR. Mixed reality, MR, bridges AR and VR, enabling digital and physical objects to coexist and interact in real time. MR devices, like the Apple Vision Pro *, use advanced sensors and pass-through cameras to blend realities. The MR spectrum ranges from augmented reality, AR minimal digital overlay, for example, smartphone filters, augmented virtuality, AV mostly virtual with real-world elements, for example, a VR meeting room with a real desk visible, true MR, seamless interaction, like manipulating holograms anchored to physical surfaces, for example, Microsoft Mesh. MR's value lies in applications like collaborative design, remote work, and interactive education. 1.4 Key differences and overlaps Aspect are VR MR environment real world and digital overlay fully virtual hardware phones, glasses, headsets immersion level partial primary use headsets, motion controllers full enhancing reality hybrid, dynamic interaction, replacing reality MR headsets, for example, Vision Pro. Variable, depends on use case, merging realities overlaps, shared technologies, sensors, LiDAR, spatial mapping, and gesture recognition. Convergence, modern headsets like Vision Pro blur lines between AR/VR/MR with pass-through modes. Applications, training simulations use VR for safety and AR/MR for real-time guidance. Chapter Summary AR, VR, and MR represent distinct but interconnected realms of immersive technology. While AR enhances reality, VR replaces it, and MR merges both, creating dynamic hybrid experiences. Understanding these foundational concepts sets the stage for exploring their technical, societal, and industrial impacts in subsequent chapters. This chapter establishes clear definitions, contrasts, and real-world examples to help readers grasp the nuances of AR, VR, and MR. The focus on practical applications, for example, retail, healthcare, ensures relevance to both novices and professionals. Chapter 2, Historical evolution of R/VR-2.1 Early innovations and sci-fi inspirations. The roots of R and VR stretch back centuries, fueled by humanity's fascination with altering perception. Early milestones include 1838, Sir Charles Wheastone's stereoscope, which created 3D illusions by merging two images, laid groundwork for immersive visuals. 1935, sci-fi author Stanley G. Weinbaum's short story *Pygmalion's Spectacles envisioned goggles offering holographic stories, a prophetic take on VR. 1950s-1960s, Morton Heilig's Sensorama, 1962, a mechanical arcade cabinet, combined 3D visuals, stereo sound, vibrations, and smells, a proto-VR experience. Sci-fi's role, works like Star Trek's Holodeck, 1970s, and Neuromancer, 1984, popularized virtual worlds, while films like The Matrix, 1999, and Minority Report, 2002, inspired real-world UI and gesture designs. 2.2 The 20th century, from Sensorama to VR headsets. The latter half of the 20th century saw foundational hardware breakthroughs. 1968, Ivan Sutherland's Sword of Damocles, the first head-mounted display, HMD, hung from ceilings and displayed wireframe graphics, crude but revolutionary. 1980s, NASA's Virtual Interface Environment Workstation, VIEW, used gloves and HMDs for astronaut training. 1990s, consumer VR's first wave, VPL Research *, founded by Jaron Lanier, sold the Data Glove and iPhone HMD. Sega VR, 1993, and Nintendo Virtual Boy, 1995, flopped commercially but kept VR in public consciousness. Cave Automatic Virtual Environment, 1992, brought room-scale VR to academia. Limitations, bulky hardware, high costs, and primitive graphics stalled mainstream adoption. 2.3 The 21st century, mobile AR and mainstream adoption. The 2000s-2020s revolutionized R/VR through miniaturization, computing power, and connectivity. 2009, AR goes mobile. R Toolkit enabled smartphone-based AR, leading to apps like LiDAR. 2009. 2012, Google Glass. 2013, debuted AR glasses, though privacy concerns and limited utility hindered success. 2016, consumer VR's rebirth, Oculus Rift, 2016, and HTC Vive, 2016, delivered high-fidelity VR, backed by crowdfunding and gaming ecosystems. Pokémon Go, 2016, became a global AR phenomenon, proving mass market appeal. 2020s, convergence of R/VR/Mr. MetaQuest, 2019 present, untethered VR with standalone headsets. Apple Vision Pro, 2023, redefined Mr. with pass-through cameras, eye tracking, and spatial computing. Snapchat and Instagram filters normalized AR for social media. Key drivers, smartphone ubiquity, 5G connectivity, AI advancements, and metaverse investments, for example, Meta, Microsoft. Chapter summary. R/VR's journey reflects a dance between imagination and engineering. Early sci-fi dreams and clunky prototypes evolved into today's sleek, powerful devices. The 20th century built the scaffolding, while the 21st century unlocked accessibility and creativity, from Pokémon Go *S Street Side Adventures to Vision Pro's spatial revolution. This historical context frames the transformative potential explored in later chapters. This chapter balances technical milestones with cultural shifts, emphasizing how R/VR evolved from niche experiments to tools reshaping industries. Highlighting failures, for example, Virtual Boy, alongside successes, for example, Oculus Rift, underscores the iterative nature of innovation. Chapter 3, Core Technologies Powering R/VR 3.1 Spatial Computing and 3D Mapping Definition. Spatial computing enables devices to perceive and interact with the physical environment, while 3D mapping creates a digital representation of real-world spaces. How it works: SLAM, simultaneous localization and mapping algorithms process data from cameras and sensors to map environments in real time and track the device's position within them. Depth sensing, LiDAR, structured light, or time-of-flight cameras measure distances to generate 3D point clouds. Digital twins, virtual models of physical spaces allow precise placement of AR objects or VR scene reconstruction. Applications: Apple Vision Pro uses LiDAR for room-scale mapping. Microsoft Mesh enables collaborative MR workspaces anchored to real-world coordinates. Challenges: computational intensity and latency in dynamic environments. 3.2 Sensors, LiDAR, accelerometers, and gyroscopes. LiDAR, light detection and ranging, role, emits laser pulses to measure distances, critical for depth mapping in R/VR. Example: iPhone Pro's LiDAR enhances AR app accuracy. Accelerometers and gyroscopes. Accelerometers track linear motion, for example, headset movement. Gyroscopes detect rotational orientation, for example, head tilting. IMUs, inertial measurement units, combine both for precise 6 degrees of freedom tracking. Applications: Meta Quest 3 uses IMUs for responsive head and controller tracking. Limitations: sensor drift over time requires periodic recalibration. 3.3 Display technologies, OLED, pass-through, and waveguides. OLED, organic light-emitting diode, strengths, high contrast, fast refresh rates, reducing motion blur in VR. Use case: PlayStation VR 2 employs OLED for immersive gaming. Pass-through mechanism: cameras capture the real world, blending it with digital content via screens, for example, Meta Quest Pro. Challenge: latency and resolution limits can break immersion. Waveguides function: thin, transparent optics that project light into the eye, for example, Microsoft HoloLens 2. Advantage: enables compact AR glasses. Limitation: narrow field of view, 50° versus human 120°. 3.4 Interaction systems, controllers, hand tracking, and haptics controllers. Examples: Oculus Touch, Valve Index controllers. Role: provide tactile input and haptic feedback for precise interactions. Hand tracking technology: computer vision, cameras, or ultrasonic sensors detect gestures. Example: Vision Pro's pinch to select gestures. Haptics range from basic vibrations, Quest 2, to force feedback gloves, haptics. Impact enhances realism, for example, simulating texture in VR. Future trends: eye tracking, Vision Pro, for intuitive UI navigation. Neural interfaces for direct brain-device interaction. Chapter summary: R/VR technologies hinge on harmonizing spatial awareness, sensor accuracy, display fidelity, and intuitive interaction. From SLAM-driven 3D mapping to waveguide optics and haptic gloves, these systems collectively bridge the physical and digital worlds. Challenges like latency, power efficiency, and ergonomics drive ongoing innovation, setting the stage for lighter, smarter, and more immersive devices. This chapter balances technical depth with accessibility, using real-world examples, for example, Vision Pro, HoloLens, to illustrate concepts. It highlights interdependencies, e.g., sensors feed spatial computing, which informs display output, while addressing industry pain points like motion sickness and field of view limitations. Chapter 4, Apple Vision Pro, a mixed reality revolution. 4.1 Announcement and Vision OS Ecosystem, 2023, announcement context, unveiled at Apple's WWDC 2023. The Vision Pro marked Apple's bold entry into mixed reality, MR, blending AR and VR seamlessly. Positioned as a spatial computer, it targets both consumer and professional markets, with a release slated for early 2024. Vision OS Ecosystem, Foundation, built on iOS/Mac OS frameworks, optimized for spatial computing with low latency interactions. Key features: familiar UI, floating windows, intuitive menus, and compatibility with existing iOS/iPadOS apps. 3D app development, new tools like Reality Composer Pro enable developers to create spatial experiences. Interoperability, AirPlay integration with Apple devices, iPhone, Mac, for seamless workflows. Developer adoption, early partners include Adobe, 3D design tools, Microsoft, Teams in MR, and Unity, gaming/enterprise apps. 4.2 Hardware breakdown, eye tracking, gesture control, and M2/R1 chips, display and optics, micro-OLED panels, 23 million pixels per eye, exceeding 4K resolution for lifelike clarity. Pancake lenses, reduce device thickness while maintaining a wide field of view, 120 degrees horizontal. Sensors and processing, M2 chip, handles general compute tasks, app rendering, multitasking. R1 chip, dedicated to real-time sensor processing, 12 cameras, 5 sensors, 6 mics, slashing latency to 12 milliseconds. Interaction innovations, eye tracking, infrared cameras and LEDs monitor iris movement for precise input, for example, selecting UI elements by gazing. Gesture control, pinch, swipe, and grasp gestures detected by sensors, eliminating need for handheld controllers. Ergonomics, modular design with adjustable headbands and prescription lens compatibility. 4.3 Use cases, productivity, entertainment, and spatial computing. Productivity, virtual workspaces, multiple floating screens for coding, design, or spreadsheets. Collaboration, FaceTime avatars with realistic facial expressions, via eyesight display, in shared MR environments. Entertainment, immersive media, 3D movies, Apple TV and content, and live sports in a virtual theater. Gaming, spatial titles leveraging Unity/Unreal engines, for example, NBA 2K24 with courtside VR views. Spatial computing, digital physical blending, place virtual objects in real-world spaces, for example, sculpting 3D models on a physical desk. Education, interactive anatomy models for medical training or historical recreations. 4.4 Market impact and competitor responses. Market positioning, premium pricing, at $3,499, targets early adopters and enterprises, contrasting with Meta's Quest 3, $499. Ecosystem lock-in, deep integration with Apple services, iCloud, Apple Arcade, strengthens brand loyalty. Competitor strategies, Meta, doubling down on affordable Quest headsets and metaverse partnerships, for example, Horizon Workrooms. Microsoft, enhancing HoloLens 3 for enterprise Mr. Azure cloud integration, defense contracts. Sony, leveraging PlayStation VR 2's gaming ecosystem to counter Apple's entertainment push. Challenges for Apple, adoption barriers, high cost and niche appeal may limit initial sales. Battery life, external pack limits mobility, 2-hour runtime. Future outlook, potential iterations, for example, lightweight Vision Air, and AR-driven features, Siri spatial commands. Chapter summary. The Apple Vision Pro redefines mixed reality through cutting-edge hardware, a robust Vision OS ecosystem, and versatile use cases. While its premium pricing and nascent developer landscape pose challenges, its fusion of Apple's design ethos and Mr. Innovation sets a new benchmark, pressuring rivals to accelerate their roadmaps. As spatial computing matures, Vision Pro's influence on industries, from entertainment to enterprise, will hinge on accessibility and third-party creativity. This chapter underscores Apple's strategic play to dominate Mr. by harmonizing hardware prowess with ecosystem synergy. By dissecting its technological leaps and market ripple effects, readers gain insight into how Vision Pro could shape the next decade of immersive computing. Chapter 5, Leading Our Forward/VR Hardware Platforms 5.1 Meta Quest Series, Dominating Consumer VR Overview. Meta's Quest line, formerly Oculus, revolutionized consumer VR with standalone, wireless headsets. The Quest 2, 2020, and Quest 3, 2023, dominate the market, offering affordability, ease of use, and a robust content ecosystem. Key features: standalone design, no PC/console required, powered by Qualcomm Snapdragon XR2 chips. Pass-through. Quest 3's color pass-through enables mixed reality experiences. Content library, 500+ titles, including Beat Saber, Horizon Worlds, and fitness apps like Supernatural. Market strategy, pricing: Quest 2, $299, and Quest 3, $499, undercut competitors. Metaverse push: Meta invests billions in VR social platforms, for example, Horizon Workrooms. Challenges: privacy concerns over Meta's data collection. Limited enterprise adoption compared to HoloLens. 5.2 Microsoft HoloLens, enterprise-focused overview. Microsoft's HoloLens, 2016-2019, targets industries with rugged, high-precision AR headsets. Key features: holographic processing, custom HPU, holographic processing unit, for real-time spatial mapping. Azure integration, cloud-powered analytics for remote collaboration and IoT connectivity. Enterprise apps, Dynamics 365 guides, training, remote assist, expert support. Use cases: manufacturing, overlay assembly instructions on factory floors. Healthcare, surgeons visualize 3D scans during procedures. Military, U.S. Army's IVAS program for battlefield simulations. Challenges: high cost, HoloLens 2, $3,500. Competition from cheaper AR glasses, for example, RealWear. 5.3 Sony PlayStation VR, gaming-centric immersion overview. Sony's PSVR 2, 2023, leverages PlayStation 5's power for high-fidelity VR gaming. Key features: OLED HDR display, 4K resolution, 110 degrees field of view, and eye tracking. Haptic feedback, headset vibrations and sense controllers mimic in-game actions. Exclusive titles: Horizon Call of the Mountain, Resident Evil Village VR. Market position: targets PlayStation's 40M and PS5 user base. Competes with Meta Quest Pro for premium VR gaming. Limitations: tethered to PS5, limiting mobility. Smaller app library versus Quest. 5.4 Emerging players: Varjo, Pico, and Magic Leap. Varjo, Focus, Ultra High-End VR /Mr. for Professionals. XR3 headset, 70 ppd, pixels per degree, LiDAR, and human eye resolution. Use cases: flight simulators, Lufthansa, automotive design, Volvo. Pico, ByteDance, Quest rival, Pico 4, 2022, offers similar specs at $429, popular in Asia/Europe. Enterprise push: Pico Neo 3 Pro targets corporate training. Magic Leap, pivot to enterprise. Magic Leap 2, 2022, focuses on healthcare and defense after consumer market struggles. Key tech: 70 degrees field of view, dynamic dimming for outdoor. Platform comparison: platform price range, audience key differentiator. Meta Quest 3 $499, consumers affordable, wireless, content. HoloLens 2 $3,500, enterprises industrial. Azure Cloud PSVR 2 $549, gamers. Varjo XR3 $6,495, professionals. PS5 integration, exclusives, best-in-class resolution. Chapter summary: the R/VR hardware landscape is diversifying. Meta leads in consumer VR, HoloLens anchors enterprise R, and PSVR 2 caters to gamers. Emerging players like Varjo and Pico carve niches with specialized use cases, while Magic Leap recalibrates for B2B. Together, they drive innovation in display tech, interaction, and accessibility, setting the stage for broader adoption across industries. This chapter highlights how hardware platforms cater to distinct audiences, from budget-conscious gamers to Fortune 500 engineers, while addressing technical trade-offs: cost versus fidelity, mobility versus power. By examining their strengths and limitations, readers gain insight into how hardware choices shape R/VR's real-world impact. Chapter 6: Software and Development Ecosystems. 6.1 Unity and Unreal Engine, building immersive experiences. Unity, strengths: accessibility, user-friendly interface, C# scripting, and extensive asset store. Cross-platform support, deploys to Meta Quest, iOS, Android, HoloLens, and Vision Pro, via Unity Polyspatial. Use cases: mobile, Pokemon Go, enterprise training simulations, and indie VR games. Tools: XR Interaction Toolkit, prefab components for hand tracking, UI, and locomotion. R Foundation, unified framework for AR Core /AR Kit development. Unreal Engine, strengths: high-fidelity graphics, nanite virtualized geometry, and lumen lighting for photorealistic VR. Blueprint visual scripting, reduces coding needs for rapid prototyping. Use cases: AAA VR games, Half-Life, Alyx, film production, virtual sets, and automotive visualization. Tools: OpenXR support, streamlines cross-platform VR development. MetaHuman framework, lifelike avatars for social VR experiences. Comparison: Aspect Unity Unreal Engine learning curve easier for beginners, steeper, Favored by AAA Studios graphics, best in class for realism, pricing good for mobile /R royalty free for small studios, 5% royalty after $1 million revenue. 6.2 AR Kit versus AR Core, Mobile AR Development AR Kit, Apple, key features, LiDAR integration, precise depth mapping. iPhone 12 Pro and later. Room Plan API generates 3D floor plans using LiDAR. Reality Kit simplifies our object rendering and physics. Use cases: IKEA Place, virtual furniture placement. Snapshot lenses with occlusion, digital masks interact with real-world objects. AR Core, Google, key features: environmental HDR, matches lighting between real and virtual objects. Geospatial API, anchors our content to GPS coordinates, for example, Google Maps or navigation. Augmented Faces, high-quality face tracking for 436+ landmarks. Use cases: Pokémon Go, location-based gameplay. Google Lens, real-time translation and object recognition. Cross-platform solutions, our foundation. Unity package bridging AR Kit /AR Core differences. 8th Wall, web-based AR framework for browser experiences. 6.3 OpenXR and cross-platform compatibility. What is OpenXR? Goal: standardize APIs to reduce fragmentation in our /VR development. Backers: Kronos Group, with support from Meta, Microsoft, Valve, and Sony. Benefits: write once, deploy anywhere, code runs on Quest, Steam VR, HoloLens, and PSVR 2. Streamlined workflows: developers avoid platform-specific SDKs, for example, Oculus SDK versus Steam VR. Key features: hand tracking, unified input model across devices. Pass-through API, consistent MR implementation. Adoption challenges: feature parity, some platforms lack full OpenXR extension support. Legacy systems, older headsets, for example, Oculus Rift S, require wrappers for compatibility. Success stories: Meta Quest, fully OpenXR compliant, enabling ports like Beat Saber to PC VR. Microsoft HoloLens 2 uses OpenXR for enterprise app interoperability. Chapter summary: the R/VR software ecosystem thrives on powerful engines, Unity /Unreal, platform-specific SDKs, ARKit /AR Core, and cross-platform standards, OpenXR. While Unity democratizes development for indie creators, Unreal pushes visual boundaries for premium experiences. ARKit and AR Core dominate mobile AR but require trade-offs between iOS and Android ecosystems. OpenXR's growing adoption promises a future where developers can focus on creativity, not compatibility, accelerating innovation across gaming, enterprise, and consumer apps. This chapter equips readers with a pragmatic understanding of tools shaping our /VR software. By contrasting engines, SDKs, and standards, it highlights how developers balance platform-specific optimization with cross-platform reach, a critical skill as immersive tech expands into every industry. Chapter 7: Industry applications of R/VR. 7.1 Healthcare, Surgical Simulations and Patient Care Overview. R/VR is transforming healthcare by enhancing training, surgical precision, and patient outcomes. Key applications: surgical training, VR simulations. Platforms like OSO VR allow surgeons to practice complex procedures, for example, knee replacements, in risk-free environments. Studies show a 230% improvement in procedural accuracy. Collaborative learning, multi-user VR environments for team-based training, for example, fundamental surgery. Surgical assistance, are overlays. Microsoft HoloLens 2 projects 3D patient scans, CT/MI, onto the surgical field, aiding in tumor removal or spinal surgeries. Real-time data. Proximi enables remote experts to guide procedures via our annotations. Patient care, pain management. VR programs like Applied VR reduce chronic pain by immersing patients in calming environments. Mental health *, VR exposure therapy treats PTSD and phobias, for example, Bravement. Challenges, device sterilization in operating rooms. High costs for hospital implementation. 7.2 Education, virtual classrooms and interactive learning overview. R/VR democratizes access to immersive, hands-on education. Key applications, virtual classrooms, VR field trips. Platforms like Google Expeditions take students to the Great Barrier Reef or Mars. Remote learning, Engage VR hosts lectures in customizable 3D spaces. Interactive learning, are textbooks, apps like Jigspace animate complex concepts, for example, volcanic eruptions. STEM labs, VR chemistry labs, Labster, let students conduct experiments safely. Professional training, VR safety drills, firefighters train in simulated wildfires, *** flame trainer ***. Benefits, boosts engagement and retention by 40%, Stanford study. Reduces physical resource costs. Challenges, equity gaps in device access. Teacher training for R/VR integration. 7.3 Retail, virtual try-ons and augmented shopping overview. R/VR bridges online and in-store experiences, personalizing retail. Key applications, virtual try-ons, fashion, Ziki, acquired by Walmart, lets users wear clothes via AR. Cosmetics, Sephora virtual artist uses AR to test makeup shades. Augmented shopping, in-store navigation, Lowe's Lobot guides customers with AR wayfinding. Home decor, IKEA place overlays furniture in real rooms using Apple Vision Pro's spatial computing. Virtual showrooms, automotive, Mercedes-Benz uses VR to showcase car models in customizable environments. Benefits, reduces return rates by up to 35%. Enhances decision-making through visualization. Challenges, requires high-quality 3D asset creation. Privacy concerns with facial /data tracking. 7.4 Manufacturing, remote assistance and prototyping overview. R/VR streamlines design, maintenance, and collaboration in manufacturing. Key applications, remote assistance, AR glasses, RealWear enables hands-free video calls with AR annotations for machinery repairs. Step-by-step guides, PTC Vuforia overlays instructions on factory equipment. Prototyping and design, VR modeling, Gravity Sketch allows engineers to create 3D prototypes in virtual space. Digital twins, Siemens uses AR to mirror physical assets for predictive maintenance. Training, VR simulations, Boeing trains technicians to assemble aircraft wings, cutting training time by 75%. Benefits, reduces downtime and operational errors. Accelerates product development cycles. Challenges, high upfront costs for enterprise-grade hardware. Integration with legacy systems. Industry comparison. Industry R-Focus VR Focus Healthcare Real-time surgical guidance Immersive training simulations Education Interactive textbooks, AR, virtual labs and field trips, VR, retail virtual try-ons, R. Virtual showrooms, VR, manufacturing remote assistance, R. Prototyping and digital twins, VR. Chapter summary R/VR is revolutionizing industries by solving unique challenges. Healthcare saves lives through precision and training. Education engages learners with immersive experiences. Retail personalizes shopping and reduces costs. Manufacturing boosts efficiency and innovation. While adoption hurdles like cost and accessibility persist, advancements in hardware, for example, Vision Pro's spatial tools, and AI integration promise scalable solutions. These technologies are not just tools but catalysts for redefining how industries operate, collaborate, and grow. This chapter underscores R/VR's practical impact, blending real-world examples with measurable benefits. By addressing both opportunity. Chapter 8, User Experience, UX, Design for Immersive Tech. 8.1 Overcoming motion sickness and fatigue causes latency, delays, 20 ms between user movement and visual feedback disrupt sensory alignment. Sensory conflict, mismatch between vestibular, inner ear, and visual inputs, for example, virtual movement without physical motion. Locomotion methods, smooth artificial movement, for example, joystick navigation, triggers discomfort. Solutions, technical optimizations, high refresh rates, target greater than or equal to 90 Hz displays, for example, PSVR 2's 120 Hz old. Low latency, use dedicated chips, for example, Apple Vision Pro's R1 chip for 12 ms sensor processing. Comfort modes, vignetting, reduce peripheral vision during movement, Resident Evil 4 VR uses dynamic tunnels. Teleportation, let users jump to locations instead of sliding, common in Rec Room. User controls, allow adjustable movement speeds and field of view, for V, settings. Case study, Oculus Comfort Ratings, Meta categorizes apps as comfortable, static experiences, too intense, roller coasters, guiding users. Challenges, balancing immersion with accessibility, for example, Half-Life, Alyx offers multiple locomotion options. 8.2 Designing intuitive gestures and menus principles, natural mapping, align gestures with real-world analogs, for example, pinching to grab in Apple Vision Pro. Feedback, use visual, highlighting, audio, clicks, and haptic, vibration, cues. Consistency, standardize gestures across apps, for example, swipe to scroll in Meta Quest. Technologies, hand tracking, Quest 3's Direct Touch allows pointing without controllers. Eye tracking, Vision Pro uses gaze for menu selection, reducing arm fatigue. Voice commands, supplement gestures with voice, for example, Hey Siri, open settings. Examples, HoloLens AirTap, a quick finger press to select holograms. VR menus, radial menus, for example, Beat Saber, minimize cursor movement. Challenges, cultural nuances, avoid gestures with conflicting meanings, for example, thumbs up varies globally. Learning curve, first-time users may struggle with abstract inputs, test with diverse demographics. 8.3 Accessibility in R/VR, inclusive design principles. Visual accessibility, text customization, adjust size, contrast, and fonts, for example, Microsoft's Seeing VR Toolkit. Color blindness modes, replace color-coded UI with patterns, for example, Pokemon Go settings. Audio descriptions, narrate visual elements for blind users, for example, *notes on blindness VR*. Auditory accessibility, subtitles and visual cues. Display sound effects as text/icons, for example, Moss uses animated captions. Haptic alternatives, vibrations for audio alerts, for example, doorbells in *Horizon Worlds*. Motor accessibility, adaptive inputs, support switches, eye tracking, or voice for users with limited mobility. Gesture sensitivity, customize recognition thresholds, for example, prolonged versus quick pinches. Cognitive accessibility, simplified UI, minimize clutter, for example, job simulators, intuitive object interactions. Guided tutorials, step-by-step onboarding, for example, first steps on MetaQuest. Case studies, XR Access Initiative, advocates for standards like audio-based navigation in VR. Walking VR, software that remaps controllers for users with limited dexterity. Design checklist consideration action item motion sickness implement vignetting, offer teleportation. Gesture clarity test gestures with diverse user groups. Text legibility allow font scaling, min 16 pt for VR. Input flexibility support voice, eye tracking, and switches. Chapter summary designing for R/VR demands empathy and innovation. By prioritizing comfort, intuitiveness, and inclusivity, creators can craft experiences that resonate across diverse audiences. Key takeaways: mitigate motion sickness, optimize tech and offer user controls. Simplify interaction, align gestures with natural behaviors. Champion accessibility, build for all abilities from day one. As immersive tech evolves, UX design will remain pivotal in bridging the gap between cutting-edge capability and human-centered utility. This chapter equips designers with actionable strategies, grounded in real-world examples and research, to create immersive experiences that are not only functional but universally empowering. Chapter 9, Ethical and Societal Implications. 9.1 Privacy Concerns, Data Collection in Spatial Environments. The privacy paradox, R/VR devices capture unprecedented personal data, including biometrics, eye/gaze tracking, Apple Vision Pro, facial expressions, and heart rate. Environmental data, 3D maps of homes, offices, or public spaces via LiDAR/sensors. Behavioral analytics, how users interact with virtual objects, dwell times, and social interactions. Risks, surveillance, employers could monitor worker focus in VR meetings, for example, Meta Horizon workrooms. Data exploitation, advertisers targeting users based on emotional responses, for example, pupil dilation during ads. Security breaches, hackers accessing spatial data to reconstruct private spaces. Mitigation strategies, local processing, Apple Vision Pro's Optic ID stores iris data on device. Regulations, GDPR compliance for EU users, plus proposed US laws like the R/VR Privacy Act, user control, opt-in consent for data collection, for example, MetaQuest's *Privacy Center. Case study, Google Glass, 2013 backlash over surreptitious recording led to redesigns and stricter privacy policies. 9.2 Digital addiction and mental health. The double-edged sword, positive uses, VR therapy for anxiety, PTSD, and phobias, for example, Oxford VR's social anxiety program. Are apps promoting mindfulness, for example, TRIPS guided meditation. Negative impacts, addiction, compulsive use of immersive games /social VR, for example, VGOT's 24/7 virtual clubs. Isolation, prioritizing virtual relationships over real-world connections. Body dysmorphia, avatars promoting unrealistic body standards, for example, Meta Horizon's legless avatars. Research insights. A 2022 Stanford study found 14% of VR users experienced post-VR sadness after prolonged use. Children at risk. Developing brains are more susceptible to overstimulation and addiction. Solutions. Time limits. Built-in usage alerts, for example, Quest 3's screen time dashboard. Ethical design. Avoid dopamine-driven mechanics, for example, loot boxes, in VR apps. Public awareness. Campaigns like *X are safety initiatives guidelines for parents. 9.3 The Metaverse, Opportunities and Risks. Opportunities. Economic growth. Virtual goods market projected to hit $200 billion by 2026, McKinsey. Global collaboration. Decentralized workspaces, for example, NVIDIA Omniverse for 3D design teams. Cultural exchange. Preserving heritage via digital twins, for example, UNESCO's VR reconstructions of endangered sites. Risks. Centralized control. Corporations like Meta or Apple dominating metaverse infrastructure. Identity fraud. Deepfake avatars or voice cloning enabling scams, for example, fake CEO in a VR boardroom. Legal gray areas. Jurisdiction disputes over virtual crimes, for example, harassment in Horizon Worlds *. Intellectual property theft of digital assets. Balancing the vision. Decentralized models. Blockchain-based platforms like Decentraland empower user ownership. Open standards. Initiatives like the Metaverse Standards Forum promote interoperability. Ethical frameworks. Proposals for a Bill of Rights for Metaverse users, for example, right to anonymity. Ethical dilemmas in practice. Example VR example surveillance are glasses recording public interactions. VR workplace analytics tracking productivity. Addiction. Pokemon Go encouraging constant play. Ownership are graffiti on private property. VR chat users neglecting real-life duties. NFT disputes over virtual land. Chapter summary. R/VR's societal impact hinges on balancing innovation with responsibility. Privacy requires robust laws and transparent data practices. Mental health demands ethical design to prevent exploitation. Metaverse must prioritize decentralization and user agency. While immersive tech promises to redefine human connection, creativity, and commerce, its risks, addiction, surveillance, and inequality, demand proactive collaboration among developers, regulators, and users. The path forward lies in guardrails, not gates, ensuring R/VR empowers without eroding trust or well-being. This chapter challenges readers to confront uncomfortable questions. Who owns your virtual identity? Can a corporation monetize your emotions? By framing ethics as a shared responsibility, it advocates for technology that elevates humanity rather than commodifying it. Chapter 10. The Future of R/VR 10.1 Lightweight Wearables and Neural Interfaces Overview. The next frontier in R/VR lies in making devices unobtrusive and intuitive. Current headsets, while advanced, remain bulky, but innovations in materials, optics, and neural interfaces promise a sleeker future. Key advancements: lightweight materials, carbon fiber, micro-OLED displays, and pancake lenses, for example, Meta Quest 3, reduce weight and size. Neural interfaces, non-invasive tech, wristbands like Meta's Control Labs decode neural signals for gesture control. Brain-computer interfaces, BCI's startups like Neuralink aim to enable direct brain interaction, bypassing controllers. Examples: Apple's patented AR glasses, rumored slim design with LiDAR for everyday use. Open Water's wearable fMRI, a headset using infrared light to monitor brain activity for VR adaptation. Challenges: battery life, balancing power efficiency with performance. Safety / regulation, ensuring neural devices are non-invasive and ethically approved. Future outlook: by 2030, our glasses may rival smartphones in ubiquity, while BCIs could revolutionize accessibility for users with disabilities. 10.2 AI integration, smarter, adaptive environments overview. AI is transforming our /VR from static experiences into dynamic, responsive ecosystems. Key innovations: real-time adaptation. AI adjusts environments based on user behavior, for example, NVIDIA's ACE for lifelike NPCs. Generative AI. Tools like GPT-4 enable natural interactions with VR chatbots or our assistants. AI upscaling. DLSS 3.0 enhances graphics fidelity without taxing hardware. Applications: personalized learning. AI tutors in VR adapt to student progress. Smart AR navigation. Context-aware overlays, for example, Google Maps Live View, blend real-time data with surroundings. Challenges: privacy, balancing data collection for personalization with user consent. Compute demands, Edge AI and 5G mitigate latency in cloud-reliant systems. Future outlook: AI-driven digital twins will create hyper-personalized worlds, while federated learning ensures privacy in adaptive systems. 10.3 Global adoption and the road to ubiquity overview. Our /VR's global reach hinges on affordability, infrastructure, and cultural relevance. Drivers of adoption: cost reduction, subsidized hardware, for example, Meta's education program for schools. 5G expansion, telecom partnerships, for example, Verizon and Microsoft HoloLens, enable cloud-based /VR. Localized content, platforms like Snapchat tailor our filters to regional trends. Case studies: healthcare in rural India, our assisted telemedicine via Microsoft HoloLens. VR classrooms in Africa, UNICEF CDU VR pilot programs. Challenges: digital divide, addressing disparities in internet access and tech literacy. Cultural resistance, adapting content to local norms, for example, modest fashion in conservative regions. Future outlook: by 2040, our /VR could be integral to global industries, from remote work to disaster response, with decentralized creators driving diverse use cases. Comparative table, our /VR evolution, 2023 versus 2030, aspect 2023-2030, projected, form factor bulky headsets, Vision Pro, slim glasses, neural wristbands AI integration basic NPCs, static environments self-learning worlds, AI companions global reach niche in wealthy nations widespread in education /healthcare chapter summary The future of our /VR is a tapestry of lightweight hardware, intelligent ecosystems, and global inclusivity. While hurdles like privacy and infrastructure persist, the convergence of AI, neural tech, and equitable access will unlock transformative applications, reshaping how we work, learn, and connect. As these technologies mature, their success will hinge not just on innovation, but on empowering humanity at scale. This chapter synthesizes cutting-edge trends with pragmatic challenges, offering readers a roadmap to navigate our /VR's evolving landscape. By anchoring predictions in real-world examples and ethical considerations, it underscores the balance required to achieve a future where immersive tech benefits all. Appendices - glossary of R/VR terms are augmented reality, digital content overlaid on the real world via screens or transparent displays. VR, virtual reality, a fully immersive digital environment experienced through a headset. MR, mixed reality, blending of physical and digital worlds where both can interact in real time. Pass-through, camera feed displaying the real world in VR/R headsets for mixed reality experiences. SLAM, simultaneous localization and mapping algorithms that map environments and track device positions. LiDAR, laser-based sensor for measuring distances and creating 3D maps. Haptics, technology simulating touch feedback, for example, vibrations, force resistance. 6DoF, 6 degrees of freedom, tracking movement in 3 axes, X, Y, Z, plus rotation, pitch, yaw, roll. Field of view, for V, the extent of the observable environment visible through a headset. Digital twin, a virtual replica of a physical object, system, or space. Metaverse, a collective virtual shared space, often interoperable and persistent. OpenXR, open standard for cross-platform R/VR development. Timeline of major R/VR milestones. 1838, Sir Charles Wheatstone invents the stereoscope, enabling 3D visuals. 1962, Morton Heilig patents Sensorama, a multisensory arcade machine. 1968, Ivan Sutherland creates the first head-mounted display, HMD, the Sword of Damocles. 1989, NASA develops the Virtual Interface Environment Workstation, VIEW, for astronaut training. 1995, Nintendo releases the Virtual Boy, a commercial VR flop. 2012, Palmer Luckey launches the Oculus Rift Kickstarter, reviving consumer VR. 2016, Pokémon Go popularizes mobile Oculus Rift and HTC Vive debut. 2023, Apple announces Vision Pro, a mixed reality headset with eye tracking and spatial computing. Resources for developers and enthusiasts, development tools, Unity, unity.com, and Unreal Engine, unrealengine.com, leading engines for R/VR content. ARKit, Apple, and ARCore, Google SDKs for mobile development. OpenXR, Chronos.org cross-platform API standard. A-Frame, aframe.io, web-based framework for VR experiences. Communities and learning, r/Oculus and r/Augmented reality, Reddit forums for news and troubleshooting. XRDC, XR Developers Conference annual event for immersive tech professionals. MIT OpenCourseWare, free courses on r/VR design principles. Hardware platforms, MetaQuest Developer Hub, developer.oculus.com, guides for Quest apps. Microsoft Mixed Reality Toolkit, MRTK tools for HoloLens development. Apple Vision Pro developer documentation, developer.apple.com/Visionos spatial computing resources. Academic journals, IEEE transactions on visualization and computer graphics. Presence, teleoperators and virtual environments. YouTube channels, Thrill Seeker, VR news and reviews. Fused VR, tutorials for Unity/Unreal. These appendices provide quick reference points for terminology, historical context, and tools to dive deeper into r/VR. Whether you're a developer, student, or enthusiast, these resources will help you stay informed and inspired in the evolving world of immersive tech.